This is Algebra 2 with trig. This is section 6.4. This is day 2. We're working with inverses and we're graphing these equations. The graph of a power function is in the form of x squared or even x cubed. And they're shown down here in our graphs. Notice that x squared graph is right there. Its coordinates would be for -2, -1, 0, 1, and 2. When you square it, you get 4, 1, 0, 1, and 4. So those would be your coordinates that go along with your graph. To figure out your inverse, which is a reflection over y equals x, this is the line y equals x. Notice that this point at 1, 1 is right on the line of reflection, so it stays right on both of the graphs. Any point that you have, we could figure out what the inverse is by reflecting it over y equals x. So we're 1 unit away and we're 1 unit away. 0, 0 is also on the line of reflection. -1, 1. If we count the diagonals, so 1 diagonal to the line of symmetry or line of reflection and 1 past it. 1, 2, 3, 1, 2, 3. So we could find all the points along it by reflecting all of these. Another way to think about that is folding the paper right along the line of reflection, and it would point over towards the right. So that would be our line of reflection. Here we have the equation as x equals y squared. That's a little confusing. We could write that as y equals plus or minus the square root of x. You take the square root of both sides, then the y is by itself. So you have your square root graph going up, and you also have your square root graph going down. It's the same thing as a parabola on its side. The other graph that we have y equals x squared. And that makes this S curve. Y equals x cubed. And I say cubed, y equals x cubed. And some points we like to use with that. I have to take 2, 1, 0, -1, -2. So when you plug it into your equation, we get 8. 1 times 1 times 1 is 1. 0, 0, 0 is just 0. -1 and -8. So if you notice, those along the way are right on our graph. Now if we reflect each one of those, they would land on our inverse, reflected over the line of y equals x. So the cubed root graph is the inverse of x cubed. A way to figure out its coordinates, y equals the cubed root graph, is to switch your x's and y's. So you notice at 1, 1 both graphs exist. At -1, 1 both graphs exist. The yellow graph is 8 over 2 up or -8 over 2 down. There's your inverse and there's your original. On this graph we showed the original. The inverse graph which would be y equals plus or minus the square root of x. That could be found either by doing the reflections, like I showed you the points, or we could take all these coordinates and just switch them. And then you could plot those points. Two different ways to figure out the coordinates of an inverse. Notice that the inverse of our x cubed graph is a function. We look at our inverse, and at any spot there's a vertical line test. It only goes through the yellow line at one location. For every x, there's only one spot for that yellow graph to be. But the inverse for x squared is not a function. Here we have our vertical line, which is a way you can test if it's a function. For each x to be a function, you only get one y answer. But if you notice, several of these x's have two different spots that it would be. It's a plus value and a minus value. If the domain of f of x is x squared, if it's restricted, that means if we limited how much it would be, so we restrict the domain to only non-negative real numbers, then the inverse would be a function. Let's go ahead and try that idea here. Find the inverse of f of x. And our equation that we're going to deal with is x squared plus 2. There's a couple different ways we could do this. We could take our function, which is x squared plus 2, and we could make a table out of that. So we look at the possible values that we could work with. So when you plug in a negative 3, you get negative 3 squared, which is positive 9, plus 2 is 11, positive 4 plus 2 is 6, positive 1 plus 2 is 3, square 0 to get 0, and then add 2, and 3, 6, 11. So we could plot those points. Also, we would hope that with an x squared graph, you would be somewhat confident of what the parent function looks like, which is a U shape, but this one's been translated up 2 units. So you should be pretty confident that you're going to have a vertex at 0, 2. You're also going to, plotting your function 1 over 1 up. When you went over 2, you'd go up 4. When x is 3, you'd go up 9. So you'd find those points. Those are here at 0, 2, 1, 3, 2, 6, and 3, 11. It's 11 units from the x-axis all the way up to your point. You would also know you have other points that are reflected over the line of symmetry. So this is another way for you to come up with the coordinates that make up this equation. But notice that this is a parabola, and if we reflect it over the line y equals x, it's not going to make a function. So we're going to limit its domain. We're only going to use the part of the graph where x is greater than or equal to 0. We often call those non-negative real numbers. So I'll connect the points of the part of the graph that we'll be using. So this is y equals x squared plus 2 with the domain of x is greater than or equal to 0. Well, if we put in our line of reflection, which is y equals x, and we reflect these points, notice that the line of reflection, which is y equals x, has a slope of 1, So when we reflect it, we're going to go at a slope of -1. It takes one step to get to your line of reflection, so we go one step past it. One step to get there, so one step past it. Two steps. Two steps. Those are the diagonals. 1, 2, 3, 4. 1, 2, 3, 4. So you can use this idea of a reflection to represent your coordinates of your inverse. What is the equation of that going to be? Well, we start with our function of being y equals x squared plus 2. We switch our x and the y. This is what we did on a previous lesson. Subtract 2, and then take the square root. Now we have to decide if this is going to be plus or minus. It typically would be, or if we're only going to use a portion of that. Well, the original graph, the domain, we could plug in positive or negative numbers for our domain, so we'd get all real numbers. But let me restrict that. We're going to restrict that to only looking at the values where x is greater than or equal to 0. The only ones that we graphed were those where x was 0, 1, 2, or 3. Our range during this portion, our range was down here at, or I guess up here compared to 0, up here at 2, and it went up from there. So it's the y values being greater than or equal to 2. Now when we do our domain and range for our inverse, we're going to switch those two values. It's still going to be x equals and y equals for the domain and range, but you switch the 0 and the 2. We're going to be greater than or equal to 2, and we're going to be greater than or equal to 0. So because the range is greater than or equal to 0, you know in fact that you're only dealing with the positive version. You're not dealing with the plus or minus, since your range is going to be greater than 0. We could, if we weren't confident with where the points were, we know that our new function, f inverse of x, is the square root of x minus 2. We could take the original points, which are 2, 0, 3, 1, 6, 2, and 11, 3. 1, 2, 3, 4, 5, 6, up 2 was a dot. 1, 2, 3, up 1. 3, 1, 6, 2, even 11, 3. So either way, there are multiple ways for us to figure out where that graph exists. So we would want to label our graph as x minus 2, the square root of x minus 2. On the second page, you can use the graph of the f function to determine whether the inverse of f is a function by applying the horizontal line test. You take the original graph and you run a horizontal line to it. If we run a horizontal line through the orange graph, it's going to cross in two spots. That tells us when we look at its inverse, it's not going to be a function. But when we cross y equals x cubed with a horizontal line, this shows that it crosses at one spot. That means a vertical line is also going to cross at only one spot. That helps us notice, without graphing the inverse, that the original graph will have an inverse that is also a function. Let's take a look here. We have a graph. This looks like the graph of y equals x cubed. We throw in this line of reflection, or I'm sorry, we throw in this horizontal line test. Notice that this horizontal line test is touching in exactly one spot. So if it touches in only one spot, then it is a function. On the contrary, if we come over here and we have our y equals x squared, it looks like, and we throw in our horizontal line, that in this case it's touching in two spots. Therefore, when you reflect it, when you curve it sideways and it opens up sideways, that this is not a function. So let's consider the function f of x equals 3x to the fifth minus 2. And we're going to determine whether the inverse of f is a function. And then we're going to figure out what the inverse is. So we're going to start out with f of x equals 3x to the fifth minus 2. You should have an idea of what an x to the fifth power graph looks like. It's odd, so you know you're going to have the graph increasing to the right and decreasing to the left using the end behaviors. But we have some numbers that we can test. If we plug in -1, -1 to the fifth power is negative, so still -1, times 3 is -3, minus 2 more gives us -5. 0 to the fifth power is 0, times 3 is 0, minus 2 more. 1 to the fifth power is 1, times 3 is 3, minus 2 more, which is 1. Now what would happen if we did 2? 2 to the fifth power. 2 to the fifth power is 32. If you take 32 and times that by 3, you get 96 minus 2 is 94. So that's why we didn't pick numbers much more further than -1 and 1, because it grows so fast in this graph. So we'll graph these 1 over, 5 down, 2 down, 1 over, 1 up, and it would take 94 by the time it actually crossed at x equals 2, and even be further down than that at -2. So there's our original graph, which is 3x to the fifth minus 2. Now we look at our line of reflection. One way to graph this is to look at the reflection points. Diagonal is only one spot away, so we're going to go one diagonal further. 2 diagonals away, so we're going to go 2 diagonals further. So this is the inverse of our original graph. Let's figure out what that inverse would be. We start out with y equals 3x to the fifth. We switch the x and the y. We add the 2. divide by 3. Now we would need to take the fifth root of both sides of the equal sign. So that's what this graph is. Y equals the fifth root of x plus 2 divided by 3. That's our equation. We could plug points in there to figure out where they would land, or we can just use the reflection. Using the reflection is a little bit more mathematical way than just plugging in our points. Notice that if this is our equation, we also know that the points that are going to work here are the reflection of our original. So we know we're going to be at -5, -1, -2, 0, 1, 1, and 94, 2. If you notice, as the graph goes out, it would have to get way out there before it actually touches 2. Here's an application problem. So in a previous lesson we talked about we do not switch the two variables in an application problem because the P in this case, or even the T for time, they stand for something specific. So you couldn't switch them and then solve for the other. You just solve for the other. The population of a town can be modeled by P equals 6,500 times time to the 0.15 power. So to solve for T, we divide by 16,500. And we're on this side we still have T to the 0.15. One way to get rid of 0.15 is to raise it to a power of its inverse, its reciprocal. So now we can say 1 over 0.15 and do that to this side also. So 0.15 divided by 0.15 is just a value of 1 for the exponent. And if you use your calculator, you'll notice that 1 divided by 0.15 is the same as 6.2 or 6 2/3. So you get 6.666667, we'll just round it to that. So this is what the time would be in terms of the population. So when will the how many years will it take if the population reaches 25,000? So we put in 25,000 divided by 1650, 16,500 actually, raised to the 6.67, and that'll come out to be approximately 15.9, which is really almost 16. So if the current year is 1998 when this was calculated, and you're going to add 16 years to that, so that's how long it takes it to get up to 25,000. That's going to be in the year 2014.